Hey guys, I'm Alex, and I'll be doing number 5 for our second video group presentation. And this question says to find the maximum value of a function f equal to the cube root of xyz, assuming that x, y, and z are positive numbers with x plus y plus z equal to k, where k is a constant. And we have to use this to show that the cube root of xyz is less than or equal to the average of xyz. And so whenever I first tackled this problem, the first thing that I wrote down were my conditions, that x, y, and z have to be positive integers, if they're greater than 0, that their sum has to be equal to k, and after we find our maximum value, keep on saying volume, that our function should be a pretty nice approximation of the average of the set. And we can use this this constraint of their sum equaling a constant k as our second function g. And so after we've determined our function f, our function g, and our constraint, we can treat this problem as we would treat any other maximizing problem, and we can use Lagrange multipliers. So then if we use the gradients of each function and we can try and find this constant, we can take the partial derivatives in each direction for each function. And so taking the partial in the x, we get xyz to the negative 2/3 over 3, it's a term from the chain rule, times the derivative of the inside. Well, this time we're deriving with respect to x, so that just leaves yz. And the partial derivative for our second function in the x direction would just be 1, because we're just deriving x. Then we take the partials in the y, we get the same outer term, xyz to the negative 2/3 over 3, but this time we take the derivative of the inside with respect to y, so we get a term xz. And for our second function g, we're once again just deriving y, which is 1. And then our final partial derivative in the z direction, that gets us once again the same outer term, xyz to the negative 2/3 over 3. And then one more time we derive with respect to z, and so we get an xy term. And with our second function, once again, we're just deriving z, which is 1. And so because all of these partials for our second function is equal to 1, we can set each partial for our first function equal to our same constant, which allows us to actually cancel these xyz to the negative 2/3 over 3's, because they're not very nice, and they wouldn't be very nice whenever we're trying to solve for all of our variables in terms of 1. But because all of our partials for the second function are 1, that allows us to set all of these equal to each other. And after doing some rearranging and some algebra, we can get a relation between each variable. So right here, yz is equal to xz, that's shown right here. If we rearrange and then do some factoring, we get that y is equal to x. And then we can use this in the second pair, xz is equal to xy. Well, actually, that could be rewritten as xz equal to x squared. Do some more rearranging, some more factoring, and then we get that z is equal to x. And so now we actually have all three variables in terms of one variable. So then we can go back to our constraint, x plus y plus z equal to a constant k. Well, we know our variables in terms of one variable now, so that would just be x plus x plus x equal to k. Algebra, some quick algebra, oh how I miss one-step algebra. We can get our variable in terms of our constant k. And now that we have our other relations, we get our other variables in terms of k. So if x is equal to k over 3, as shown here, that means that y is equal to k over 3, and that also means that z is equal to k over 3. And these 3 points are where our function is going to be maximized. So if we plug these points back into our function, we would actually get a root. K over 3 times k over 3 times k over 3. K to the third, k cubed, and 27 are both perfect cubes. And so they simplify to a root, k over 3. Here's our maximum value right here, k over 3. And this maximum value just happens to be the average of the data set, because the average of the set would just be the sum of the set, which is k, it's given in a constraint in our problem, divided by how many variables we have, which is 3. And so by showing that these two are the same, we can actually write this function, this function is an approximation of the average. And if we generalize this concept, we can see that this is true for more than 3 variables too. If we keep the same general constraints, that the variables have to be positive integers, that their sum has to be equal to k, and that their geometric mean, or all of the variables multiplied times each other, and then we're taking a root, an nth root that is the same number as the number of variables we're including in the set. If we keep those constraints, we can see through the Lagrange multipliers that these relations are going to be very similar. This outer term from integrating the chain rule, it will be most likely even uglier. But the partial derivatives from our constraint aren't going to change. So that means that all of these ugly terms will still be able to cancel out, and instead we'll have the intermediary terms instead, but with 3 variables instead of 2 if you were using 4 variables up here instead of 3. And then you can do some more algebra and more rearranging to get all of the variables in terms of 1 variable. Use your constraint to solve for that 1 variable in terms of your constant, get your maximized points, and then plug those points back into your original function to find your maximum value. And that value is always going to be the average of the set. Oh, sorry, I almost choked on my spit. Nice. But this is really cool. I did not see how this could come together until coming to the very end of the problem, where I immediately thought, actually, what happens if we have more than 3 variables? What if we had 4 or 5 or 10? Well, if we keep those general constraints like we discussed, this root that we get for trying to find our maximum value of our function is always going to be the sum of the data set, because the average of the data set, because the average of the data set is just going to be the sum of the set, which we constrain to a constant k, divided by however many variables we use, which changes depending on how many variables we use. Yeah. And so then we can get an approximation for, say, the 4th root of w, x, y, z, the 6th root of the last 6 letters of the alphabet, or any 6 letters that you want to use. It can always be an approximation of the average of the set. I just thought that was really cool, and I hope you guys think that that's pretty cool too. I hope I could help you understand it a little bit more.